At the end of this video, I hope that you can describe dipole-dipole forces, hydrogen bonding, induced dipoles, and London dispersion forces, as well as their effects on properties such as boiling and melting points, and then explain the shapes of molecules or polyatomic ions using VSEPR theory. Chapter 6, Section 5, Intermolecular Forces. As a liquid is heated, the kinetic energy of its particles increases. At the boiling point, the energy is sufficient to overcome the force of attraction between the liquid's particles. The particles pull away from each other and enter the gas phase. Boiling point is therefore a good measure of the force of attraction between particles of a substance. The higher the boiling point, the stronger the forces between the particles. The forces of attraction between molecules are known as intermolecular forces. Intermolecular forces vary in strength but are generally weaker than bonds that join atoms and molecules, ions and ionic compounds, or metals and solid metals. Compare the boiling points of the metals and ionic compounds in Table 6-7 on page 190 of your text or on the screen now with those of the molecular substances listed. Note that the values for ionic compounds are much higher than those for molecular substances. Molecular polarity and dipole-dipole forces. The strongest intermolecular forces exist between polar molecules. Polar molecules act as tiny dipoles because of their uneven charge distribution. A dipole is created by equal but opposite charges that are separated by a short distance. The direction of a dipole is from the dipole's positive pole to its negative pole. A dipole is represented by an arrow with a head pointed towards the negative pole and a crossed tail situated at the positive pole. The dipole created by a hydrogen chloride molecule, which has a negative end at the more electronegative chlorine atom, is indicated on the screen now. The negative region in one polar molecule attracts the positive region in adjacent molecules, and so on throughout a liquid or solid. The forces of attraction between polar molecules are known as dipole-dipole forces. These forces are short-range forces acting only between nearby molecules. The effect of dipole-dipole forces is reflected, for example, by the significant difference between the boiling points of bromine fluoride, BrF, and fluorine, F2. The boiling point of polar bromine fluoride is negative 20 degrees Celsius, whereas the nonpolar fluorine is only negative 188 degrees Celsius. The dipole-dipole forces responsible for the relatively high boiling point of bromine fluoride are illustrated schematically in figure 6-25 on page 191 of your text or on the screen now. The polarity of diatomic molecules such as BrF, bromine fluoride, is determined by just one bond. For molecules containing more than two atoms, molecular polarity depends on both the polarity and the orientation of each bond. A molecule of water, for example, has two hydrogen-oxygen bonds in which the more electronegative oxygen atom is the negative pole of each bond. Because the molecule is bent, the polarities of these two bonds combine to make the molecule highly polar, as shown in figure 6-26 on page 191 of your text or on the screen now. An ammonia molecule is also highly polar because the dipoles of the three nitrogen-hydrogen bonds are additive, combining to create a net molecular dipole. In some molecules, individual bond dipoles cancel each other out, causing the resulting molecular polarity to be zero. Carbon dioxide and carbon tetrachloride are molecules of this type. A polar molecule can induce a dipole in a nonpolar molecule by temporarily attracting its electrons. The result is a short-range intermolecular force that is somewhat weaker than the dipole-dipole force. The force of an induced dipole accounts for the solubility of nonpolar O2 oxygen in water. The positive pole of the water molecule attracts the outer electrons of an adjacent oxygen molecule. The oxygen molecule then has an induced negative pole on the side toward the water molecule and an induced positive pole on the opposite side. The result is an attraction to the water molecule, as shown in figure 6-27 on page 192 or on the screen now. Hydrogen bonding. A particularly strong type of dipole-dipole force explains the unusually high boiling points of some hydrogen-containing compounds, such as hydrogen fluoride, HF, water, H2O, and ammonia, NH3. In such compounds, the large electronegativity differences between hydrogen atoms and the fluorine, oxygen, or nitrogen atoms makes the bonds connecting them highly polar. This gives the hydrogen atom a positive charge that is almost half as large as that of a proton. Moreover, the small size of the hydrogen atom allows the atom to come very close to an unshared pair of electrons in an adjacent molecule. The intermolecular force in which a hydrogen atom that is bonded to a highly electronegative atom is attracted to an unshared pair of electrons of an electronegative atom in a nearby molecule is known as hydrogen bonding. Hydrogen bonds are usually represented by dotted lines connecting the hydrogen-bonded hydrogen to an unshared electron pair of an electronegative atom to which it is attracted.
Hydrogen bonding. Hydrogen bonding is the intermolecular force in which a hydrogen atom that is bonded to a highly electronegative atom is attracted to an unshared pair of electrons in an electronegative atom in a nearby molecule. In a solution of pure water, the hydrogen atoms bonded to an oxygen atom are attracted to a lesser extent to the unshared electron pairs of neighboring oxygen atoms. This attraction between molecules results in a boiling point that is higher than usual.
The effect of hydrogen bonding can be seen by comparing the boiling points in table 6-7 on the screen now, also on page 190 of your text. Look at phosphine, pH 3, compared to the hydrogen bonded ammonia, NH3. How does hydrogen sulfide, H2S, compare with strongly hydrogen bonded water, H2O? Well, the H2S boils at a much lower temperature than does H2O. This is explained by the fact that sulfur is not nearly as electronegative as oxygen. So, hydrogen bonding between H2S molecules is much weaker than it is in H2O molecules. London dispersion forces. Even noble gas atoms and molecules that are nonpolar experience a weak intermolecular attraction. In any atom or molecule, polar or nonpolar, the electrons are in continuous motion. As a result, at any instant, the electron distribution may be slightly uneven. That momentary uneven charge creates a positive pole in one part of the atom or molecule and a negative pole in another. This temporary dipole can then induce a dipole in an adjacent atom or molecule. The two are held together for an instant by weak attraction between the temporary dipoles, as seen in figure 6-29, or on the screen now. The intermolecular attractions resulting from the constant motion of electrons and the creation of instantaneous dipoles are called London dispersion forces, after Fritz London, who first proposed their existence in 1930. London forces act between all atoms and molecules, but they are the only intermolecular forces acting among noble gas atoms, nonpolar molecules, and slightly polar molecules. This fact is reflected in the low boiling points of the noble gases and nonpolar molecular compounds listed in table 6-7 again. Because London forces are dependent on the motion of electrons, their strength increases with the number of electrons in the attracting atoms or molecules. In other words, London forces increase with atomic and molar mass. This trend can be seen by comparing the boiling points of the gases helium, He, and argon, Ar, hydrogen gas, H2, and oxygen gas, O2, and then chlorine, Cl2, and bromine, Br2. At this point, I hope that you can describe dipole-dipole forces, hydrogen bonding, induced dipoles, London dispersion forces, and their effects on properties such as boiling and melting points, and then explain the shapes of molecules or polyatomic ions using VSEPR theory.